Let's get started. So we discussed a lot of different topics so far. All right, let me see if I can somehow get this thing out of the way. Maybe not. Oh well. So what I thought I'd do today is to go through some of the active research topics right now. I won't go into that much breadth. There's many more research topics, but I thought it would be good to highlight a little bit what's happening right now in the field of reinforcement learning, deep reinforcement learning, and maybe also give some pointers to what would be interesting still to do. There are some notable things missing here, which maybe might disappoint some of you. For instance, I won't be talking about multi-agent learning, which is very interesting and hard, but it's also a very big topic, and there's lots to be discussed in that respect. And I thought about doing it, but I don't think I could give it a fair enough overview in the amount of time I still have left. But before I dive in, I just wanted to give a quick overview, basically to remind you of all the stuff we've already discussed, and it's quite a lot actually. So this is basically per lecture. I skipped over the introduction lecture here, which contained some material, but it also was covered again in later lectures, which means there were basically 6 lectures so far with technical contents, let's say. The first one was on learning how to make decisions, and we focused on bandit problems in which there's a single state, but there's multiple actions, and there's already a trade-off there between exploration and exploitation. Also because each action you make determines what data you see. If you take an action, you'll get data for that action, but not for the other ones. And we discussed greedy and epsilon greedy algorithms. We discussed policy gradients, which you can already discuss in that context, and upper confidence bound algorithms, which are in some sense optimal in those settings. Then, of course, we moved in the second lecture to sequential decision problems. We discussed Markov decision processes, how to plan in these with dynamic programming, and also the general framework of policy evaluation plus policy improvement, which then together is called policy iteration. And that's more general than dynamic programming, although these terms are often used in the context of dynamic programming. The idea of doing policy evaluation and then doing policy improvement in order to get good policies is very general and basically underpins most of the reinforcement learning algorithms for finding optimal policies. So then we wanted to get rid of the assumption that you could have your model, so we went to model-free prediction and control, in which we discussed Monte Carlo returns, where you just follow a certain policy for a while until a termination of an episode, and then you look at the return and you use that basically as, you could say, a supervised target. You're doing regression towards these returns to estimate the value of that current policy, and then you could separately still do the policy improvements, which together again gives you policy iteration, and this allows you to learn. And then we discussed other ways to do that, for instance by using, or maybe most notably by using bootstrapping in temporal difference learning and the control variants of that, Q-learning, SARSA, and double Q-learning, and other related algorithms. We also discussed the distinction between on and off policy learning, where on policy learning is what you might most naturally do in a Monte Carlo setting, although you can do off policy learning there. But it means collecting data according to your current policy, thereby estimating that current policy, and then maybe later deciding how to improve it. But you could also do off-policy learning. For instance, this is what Q-learning does, which learns immediately about the greedy policy with respect to your current values, which allows you to more quickly optimize, in many cases at least. But it's a more general distinction. You could also just have some data, you're interested in a certain policy, but the data was generated with a different policy. For instance, humans did some things in a certain domain and you want to learn from that, but you want to see what would happen if you would do something else. This would also be off-policy learning. So the learning about a greedy policy is a specific case of off-policy learning. And I mention that because sometimes people conflate these and they say off-policy learning, but they mean specifically to learn about the greedy policy, which is indeed off-policy, but it's not the only way you could be off-policy. So then, of course, we discussed function approximation and what these days is now called DPRL often. because this is the combination of deep neural networks as function approximation within a reinforcement learning context. And we discussed the distinctions between tabular representations, linear representations, and nonlinear representations. Also touched a little bit about, on convergence and divergence in these settings. We've seen very small toy examples in which you can get these algorithms to diverge if you basically do it wrong, if you're not careful. There are some fundamental issues there, and it's important to understand these examples. In practice, however, if you're careful with how you set up these systems, they do work, and they don't go off into weird solutions that often. We also discussed least squares prediction, which is most notably useful when you have a linear function approximator, because then you can do, basically you can exploit the fact that it's a linear function approximation to learn more efficiently, although it comes at the cost of some compute. These least squares methods, if you have n features that you're learning from, so your value function is a linear function from some feature vector, and this feature vector has n components, then these least square methods, they take n squared compute, whereas if you do a TD learning method, it would typically only take n compute per update step. That said, these least squares methods, they tend to be more data efficient though. So if your feature vector is fairly small and you can get away with using just a linear function, and the data is more expensive than the compute to do the updates, which is quite often the case, then you should perhaps consider using these least squares methods. We also discussed multi-step returns, and I'll return to that in this lecture as well. Neural Q-learning, and as a specific instance of that, DQN, which is short for deep Q networks, but it's also, so it's a generic term in a sense, when you have a deep network that represents a Q function, but DQN has also come to refer to the specific algorithm that was run on a suite of Atari games and got good performance there, which used indeed a deep neural network to represent the the action values. But it had a couple of other components as well. Okay, so then we discussed how to learn policies directly instead of going through a value function, or to use them in addition to a value function. In the policy gradients and actor critic methods lecture. So reinforce is an algorithm you can use to just learn a policy. You could add a baseline or bootstrapping or both to reinforce, which means you might still be using a value function, and then we typically call these things actor critic methods. There are other ways to use value functions. In this context, we call the policy the actor and the value function the critic, which is just the terminology that has been used for these things. And within this context, we also discussed ways to make these things more efficient. For instance, by using trust region methods, which means that you don't update your policy too much. You stay somewhat close to your current policy in a sense, which can lead to smoother trajectories, better learning. And we discussed how to use these methods to do continuous actions, because that turns out not to be that hard when you're already in the space of learning these policies directly. And we discussed some specific methods. And then last lecture, we focused on learning from a model. We talked about the differences between different types of models. You can have a full model, which basically means you're learning the whole MDP, and then you could just do dynamic programming on that. You can have an expectation model, which means you're only learning the expected state, not the full transition dynamics. You're not interested in the distribution of the transition dynamics, but you're interested in maybe predicting a next state. And we discussed the stochastic or generative models, in which you implicitly learn the distribution in a sense, which you can then sample from, but you don't have the explicit access to the distribution perhaps. And then you can just use this as a simulator, for instance. You could still chain the model together. You could do an update through your model. You put a state in and a state comes out, and you could put that into your model again and you get a next state. You could create a whole trajectory in that fashion and maybe use that to learn from. And then we discussed the DYNA algorithm, which essentially means that you're using a model to generate more data, whichever model you're using, a full model, an expectation model, or a stochastic model. And then you're using that data to learn your value function from. And in typical DYNA, you're also using the raw data that goes into your learning your model also directly to update your value function. Importantly, we discussed the distinction between parametric and non-parametric models, where maybe the clearest example of a non-parametric model is if you store your experience. You store your transitions that you've seen, which you can then later access again. And we discussed how this is a non-parametric model in the sense that you can still query this. You could still ask for a certain state in action, what was the next reward and next state, but it will just return you whatever you saw in that situation, rather than some prediction of what you might see. Which also means that you can of course also only query states and actions that you've actually seen. But then it does really work quite well, and I'll also return to that in this lecture. So in that case, we call this experience replay if you sample from this non-parametric model. And at the end there, we discuss search and specifically Monte Carlo tree search a little bit. But I actually won't return to that much in this lecture. So if you have any questions about any of these topics, of course, feel free to interject. So the main topic today would be about what are some advanced topics, what's some active research to give you a flavor of what's going on, and what are the open questions as well. And to start, it might be good to pop up to the high level and to consider what is the main question that we're trying to answer. And for instance, we could pick how do we maximize future rewards. I say for instance because it's the question that I'm personally most interested in, but you could actually imagine other questions which are related to reinforcement learning, such as how can I learn to predict certain things about different policies in the context where you have a lot of data. So you might do off-policy evaluation as a specific thing that you might be interested in, not just for control, not just to maximize reward, but maybe to understand a certain problem. But let's say you're interested in maximizing, so we're interested in finding good policies, then you could imagine some sub-questions which are still fairly general, which include what do we learn? Do we learn values, models, policies, all of these? Also, how do we learn this? For instance, do we use TD or Monte Carlo to learn a value function? And we've seen some trade-offs. It's not always immediately clear how to do this most efficiently. And sometimes you just have to try, see what works. There's also the question how we represent the learned knowledge. A lot of people these days use deep neural networks to represent these, but in some cases it's actually more appropriate to store things in a non-parametric way. Just store some samples. You could in addition store things in linear functions sometimes, which has the advantage that these things are typically quite robust and you can learn them very quickly, but of course they have limited capacity. So it really depends on what you're trying to learn and whether this function class that you pick is flexible enough to learn what you want to learn. And the deep neural networks have definitely have the benefit of being quite flexible, so they are able to represent many functions, which is why they're used so often. And then, of course, the last question, which maybe is also one of the first to ask, is how do you use the learned knowledge? Because if you don't know how to use it, why are you learning it in the first place? So maybe you should think about this first before you decide what you do. And sometimes it's more in reverse, where people focus, say, on value-based methods without even thinking about whether they are most interested in these values or whether in the end they're more interested in the policy, say. Now, there's many specific open research topics. This is not intended to be a full list at all, but some important topics include exploration in the full sequential case, because we've discussed some advanced exploration techniques in the first lecture on bandits, well, second lecture actually, the first lecture with substantial technical contents perhaps. But a lot of these ideas don't naturally or easily transfer to the full sequential case where you're doing function approximation. For instance, to give a clear example of this, the upper confidence bound algorithm that works really well in bandits requires you to keep track of counts. And these counts, they basically count how often you've selected a certain action. If you can do that, that's very powerful, and you can basically use that to get a measure of how uncertain you are about the value of that action, which allows you to be optimistic in the face of uncertainty and pick the actions that either have a high value, expected value right now, or you're very uncertain about. And especially actions that both have a high value and you're uncertain about, you'll pick them, and then either your estimate will be correct and your uncertainty will just decrease, or you'll find out that your estimate was too high and maybe the value will decrease and maybe your uncertainty remains high. But in the end, this all evens out, and it turns out if you do that, you're almost optimally exploring, in the sense that the long-term regret that you accumulate using that algorithm is basically as low as you could get it. However, counts are fairly hard to do when you're in a complex situation where you're relying on function approximation, because in these settings we want to generalize, which is good. We want to be able to see in a new state, we want to say immediately get a good estimate for the value of that state. But we don't necessarily want these counts to generalize, because it might look like a similar state, but you're not 100% sure it's a similar state. So maybe you want to have these counts be a little bit more specific, and that turns out to be relatively hard to do with deep neural networks. There has been some work, which I'll not touch upon too much. I'll mention one example, but there's much more out there, in which people have been able to get this to work better, and also to get more maybe advanced exploration working. But it remains an open topic how best to do this. Another topic is credit assignments, which maybe is intuitive, where you can have problems in which it takes a very long time before you actually see the outcome of an action. You might take an action that leads you into a certain corridor, but only way, way further do you actually get the reward of going there. And how do you then correctly assign the credit for that decision of going left or right all the way back through time to that specific situation? Now, the long-term predictions already capture this in a sense, but it might mean that your signal is very noisy. And in addition, if you're exploring in the meantime, there might be lots of actions that you took which actually were not that relevant for the reward, but there's no way for the algorithm to really know this by just looking at the data. So this is also still an open topic, how best to do this. Another thing related to the previous lecture is how to plan with inaccurate models. We talked about this a little bit. If you have a full accurate model, you can just plan using, say, dynamic programming if it's a small enough model, or maybe using something like Monte Carlo tree search if the model is too big to go through the full model. But planning has the tendency, especially if you use these classical planning techniques, which are very good for these true models, it has the tendency to find an optimal policy that exploits the model in any way possible. So if there's an inaccuracy in your model, it might just exploit that too much, and it might find policies that basically walk through walls where you can't actually, because the model is slightly inaccurate and it thinks there's a door there, which might be the wrong thing to do. And it's still somewhat of an open question also, or maybe it's quite a big open question, how to best use models if you know these models are either partial or inaccurate. Now, of course, there's always more work possible in sample efficient learning, because a lot of the algorithms that we use these days still use quite a lot of samples. Maybe this is related to the previous point. If we can learn these models, maybe we can be more data efficient. This used to be the case in when we were doing smaller RL problems, but it hasn't really transferred yet to the deep RL case. Maybe a fairly generic thing is how to appropriately generalize. This doesn't necessarily just apply to the reinforcement learning case. But one way to think about this is, especially if you have a long, big problem. Let's think of an agent with a long lifetime. This agent will find itself in new situations again and again if the world is sufficiently rich and complex. But the situations will resemble each other in some way. And specifically, the situations might be composed of different parts that you've seen before. For instance, if you're taking courses at UCL, you might find yourself in a completely new room every once so often for a lecture. But you know what a room is, you know where to find a seat, you know how all of these things work, right? Because you can generalize from these past experiences. It doesn't require you to be in exactly the same place again in order to be able to do something. And this means that we generalize appropriately. And the way we typically think about how we do that is that we have something which maybe is a little bit akin to a symbolic representation, where we can think about a chair and maybe a laptop, and we can even think of some abstract things like a course or a specific lecture as a thing, and we can reason about these, and we can combine these things together. We can talk about taking a tube to a lecture, where both of these are actually fairly high-level abstract concepts. And then the question is, how do we learn these? How do we learn these things from raw data? Or is that even actually what's happening at a low level, say, in your brain? Or is the symbolic nature of it, is that something that is our explanation of what's happening? There's something strong about symbolic knowledge, though, which is that it's quite easy to combine these things compositionally, as we also do, for instance, with language, where we can combine different words together to form new meanings, and we don't have to relearn the meaning of every sentence that we might hear. So this is still an open question as well, how to best do this, and also how best to combine this with learning from very low-level sensory motor inputs, say pixels and such. And this is related to the last point, where we want to build a useful, general, and information-rich agent state. We haven't talked about that much, but your agent state needs to also incorporate, for instance, memory. You need to have some context of what you're doing. We did discuss it, but we didn't really talk about solution methods for this. Okay, so there's loads still to be done. So we haven't finished like how to solve the full reinforcement learning problem. That's basically what I'm saying here. But I think it might be useful to go into a specific case study and to discuss something that has been done concretely, which might give you a flavor of how we're trying to approach these problems and how we're trying to just improve things. And specifically, I'll talk about something that we, by the way, sorry, I should preface this by saying I'll talk about things that I know well, so it's research that I've worked on myself mostly, just because I know it better. Doesn't mean that this research is necessarily more important or more interesting than other research out there. But I wanted to walk through an agent that we recently built, which we called Rainbow DQN. This was, by the way, in collaboration with Hado Van Hasselt, who gave the TensorFlow lecture at the beginning of this course as well. So you've seen him. And the starting point here was the DQN algorithm, which I think, yeah, I have in a slide or two. So I'll tell you again what's in there. Which is basically Q-learning with deep neural networks, including target networks and experience replay. But that includes several additional components. And these were double Q-learning, parameters replay, dueling network architectures, which means we're splitting the values, state values from the action advantages. I'll talk about all of these, so I'll explain what that means. Multi-step updates, this is in yellow. I was aware that this probably wouldn't show up well on the slide, but I still wanted to keep the nice rainbow color going there. So apologies for that. Distributional reinforcement learning and parameter noise for exploration, which is also sometimes called noisy networks. And then we combined all of these components into an agent also to see what happens, but to also understand the components better, because each of these was basically proposed in a separate research paper, just looking at that specific component and then showing, well, this might be an interesting thing to look at. But then combining them is not necessarily as good, or the different components don't necessarily combine well. So it was an open question whether they would. And so that's basically what we did. We combined them, we looked at performance, we looked at how the performance depends on all of these components, just to understand better how all of these things come into play. One thing I want to mention here is that some of these you could think of as changing the reinforcement learning to be more aware of the fact that we're using, say, deep learning techniques and standard, more or less standard deep learning optimizers under the hood. Sometimes it's better to change your algorithm a little bit. For instance, to change your loss a little bit, to be aware of that, so then it works better. This was part of the motivation of using experience replay and target networks in the first place in DQN. And in other cases, we might even change the deep learning side a little bit. You could think of it as that. So you could call this deep learning aware reinforcement learning on the one hand, and maybe reinforcement learning aware deep learning on the other hand, where maybe we want to think about this, how do these things combine? And that's also still somewhat of an open question, because a lot of the deep learning techniques that we rely on were mostly proposed and investigated at depth in, say, classification tasks, which are quite different in nature than the, especially than the online reinforcement learning setting. I've mentioned this before. For instance, one clear distinction is that in reinforcement learning, we're actively collecting our data and we're changing how we collect our data by changing our policy, which means everything's non-stationary. So we're violating one of the standard assumptions that is made in supervised learning. So then, of course, we have to be careful that we check that the methods that were proposed in that setting still apply and that they still work. So I'll step through each of these components, but first, let me explain the benchmark. So I think a lot of you are familiar with this. I also mentioned this earlier in the course, but I just wanted to stop here and be a bit more explicit about it. So the domain here is something called the Arcade Learning Environments, or the ALE, which allows you to play with Atari games. And this has become quite a common benchmark. For instance, it's also available within the OpenAI gym. And it's nice because it has a diverse set of Atari games, which are fun and interesting for humans. That's why they were designed. So this means that they might be an appropriate test domain if we want to compare how these algorithms compare to what, say, humans might do. And they might also be a good level of difficulty to test algorithms. I think we found this in the past by doing research on this, that typically if you find that things that work well across many domains, it's typically just a good idea. And it might apply more generally. Also, what's very nice about this is that it's a simulator, which is easier to work with, say, than a real robot. So this is good to test ideas. Of course, if you're interested in doing things in, say, real-world robotics, then you still have to check whether these ideas still transfer there. But again, we found that most of the ideas that work really well in simulated settings, they might also work pretty well in other complex settings. Maybe one caveat here is that these Atari games, a lot of them are quite reactive, which means that memory isn't that big a component. So we found that agents that don't really have a good memory component can still do quite well on many of these games, because you basically can just look at the screen and you know everything that you need to know. So that's maybe a limitation of the benchmark. There are some games in which you might need memory more than others, but maybe for specific, if you want to look at agents that have to use memory, you might want to consider being careful about which tasks you select. The goal is to build a general learning algorithm without game-specific knowledge. So the typical setup is here, that we take a learning algorithm and we train it on each of these games separately. It's the same learning algorithm with the same hyperparameters and everything, and it needs to be able to learn each of these games. This is different from another thing that you could imagine, which is to take one learning algorithm and to run it on all of the games at the same time. This is something you could also do, which is maybe a harder task. And then you could also consider all of the games together maybe to be one thing that you do, one task, rather than to consider each of these games to be a separate task. Both of these are valid things to do, but this is the one that we're doing where we're training it like from scratch from each of these games, and then we're checking how well the algorithm does. This is also what was done for the original DQing work. We will allow some Atari-specific knowledge. For instance, the size of the inputs are fixed across these games, which in the typical case is a downsampled version of the game to 84 by 84 pixels, which is then fed to the agent. In all of these games, it's exactly the same. So we're not considering how to deal with, say, non-uniform observations. But it's fairly mild knowledge, and we're not putting any, basically we're not putting a lot of solution-related knowledge in there. We're just putting in some structure that allows us to play on all of these games, but we're not telling it what the actions mean or even what the agent is in each of these games. So the question is, can we build an agent that plays well? And the starting point is the DQing algorithm. To recap, it includes a convolutional neural network, which takes these pixels input. It actually takes a stack of a few frames of pixels. This is important because it doesn't really have a memory component otherwise. And for instance, in the game of Pong, you have to hit a ball from one side to the other. And if you don't have a couple of frames, you can't tell which way the ball is going. So that might make it harder to predict an accurate value. But if you just stack 4 frames, say, then you can basically see which way the ball is going. So it's not a strong form of memory, but it's enough to detangle these things. This maps into a vector of the same size as the number of actions that you have. So this is a discrete action set. These games have between 3 and 18 actions, and we basically just output a vector with the appropriate number of elements, which means for each state we gave you all the action values, and then you can just grab the relevant one to update. This is combined with an epsilon greedy policy, which is quite maybe an unsophisticated way to explore, but it works quite well regardless. Experience replay. So we have a replay buffer in which we store past transitions. This typically has some windows, so at some point you start throwing away all transitions when you add new ones. And then you just sample from that uniformly to update your network. It's not quite Dyna, because in this setting we're not actually using the fresh data to update the network, which Dyna proposes that you should be doing, and maybe you should be doing. It's unclear. It's maybe an easy thing to try. There's a target network, which basically means we have a copy of the parameters, which we keep fixed for a while, as it says on the bottom, for say 10,000 steps, or maybe 2,000 steps. This is the parameter you can set. And then every once so often you just copy in the latest online parameters into this parameter vector. And this is used in the bootstrapping. So when you want to see the value of the next state, you use those parameters instead of the online parameters. The idea of which being that it keeps your target a little bit more fixed, and this might make the learning easier. And it was found in the original work that this helped. Then we have a loss. This is one-step Q-learning in this case, using that target network. And we have an optimizer that minimizes that loss. There's a stop gradient on the value at the next state, which I put here for completeness. But if you consider this a loss of the online parameters, the next state value doesn't even actually depend on those parameters directly because it's using the target network parameters. But just for clarity, the stop gradient is still there. And then you just use some optimizer. In the original DQN work, this was RMS prop. So that's DQN. And then the first component is basically double DQN, so I can be very quick about this. There's already a target network, so we already have two networks, which you need to do double Q learning. So what we'll do here is we'll pick the maximum action according to the online network, and we will evaluate that according to the target network. And this gives you a form of double Q learning, which you can then plug in, and this gives you then what you could call double DQN. And this was shown to give you a healthy boost in performance already, because apparently in some of these games the overestimations were quite pronounced, which would hurt performance. I assume this is roughly understandable because we covered double Q learning before, but stop me if anything's unclear. Okay. Next components, prioritize replay. This is related to our previous lecture, where one thing that we notice is if you have a model, you might want to actively query this model. You might want to think about which things you grab from the model. This applies when you're doing Dyna, when you want to generate some data from your model to learn from, then it might be appropriate to think about which data do you want to generate. And prioritize replay gives you an answer to that, where the idea is to prioritize transitions on which you can learn much. Now, how do you know you can learn a lot on a certain transition? Well, one way is to look at the magnitude of the loss on the previous time you looked at that transition. Because if this magnitude is high, that means that when you would do an update with this transition, that the gradients would, the gradients would also be high, and you would change your parameters in your network quite a bit. Now, before implementing this or trying this, you might think, maybe there's a caveat. Maybe this is actually the wrong thing to do because maybe the loss there is high because it's just intrinsically very hard to learn that. And this might still be true in certain cases. But it was found, at least in this setting for DQN, that this is a very good signal. And if you prioritize your updates according to this signal, then you get much better, higher quality updates, you get much faster learning. And this might be related to the fact that the deep neural network isn't actually that big for like common day deep learning standards, but it still has millions of parameters, which might be quite a lot for these Atari games. So the network in some sense might have sufficient capacity that you should be able to suppress the loss pretty much everywhere, at least up to a degree. And if that's the case, then it can't really hurt to try to actually learn everything. If you're in a different setting where certain things are just intrinsically hard and you might never learn them, maybe it's the wrong idea to focus too much on them. But here it's perfectly fine, turns out. There are some additional design choices. For instance, I put like a bullet point there that says sample according to the priority. So we're not actively like picking the highest priority sample. No, we're actually ranking basically the experience in the replay buffer according to the priority, but then we're still sampling to get some diversity in the typical case. And there are some parameters involved in that. How much do you sample? How much do you care about the priority compared to being a little bit more uniform? Some design choices there, which might be important to push performance up. But the main idea, if you just implement a fairly vanilla version of this, it should already help. So the main idea is just the prioritization, and that's the important bit, perhaps. Okay. So the next component. So again, I'm going fairly quickly through these components, so just feel free to stop me. In the next component, we're going to do something which you could call reinforcement learning aware deep learning, which is maybe a simple idea if you think about it in hindsight, which is that you can think of these action values as decomposing into separate parts. For instance, you could think of them as decomposing into a state value part and an advantage part, where this advantage now is basically the advantage of taking that action in that state. And one way you could set it up is to basically change your architecture a little bit, where you have a separate stream that goes into a value and a separate stream that goes into an advantage vector, and then you just add these together to give you your action values. There was an additional bit here which is missing from the slide, which is that this gives you an additional degree of freedom. Normally, let's say you have 10 action values. You should then also have 10 advantages, and you have 1 state value. So now you have 11 values to learn. That might not seem so much of a problem, but it actually means that the state value can go up arbitrarily, and then all of the action advantages can go down arbitrarily, and this might cause some instability, or the other way, of course. And it turned out to work better if you subtract the mean advantage from this, which basically means that we're telling the state value you should basically consider the advantages to be on average 0, and then you should be estimating the state value conditioned on that. So you're really trying to estimate the real state value in some sense. And then these advantages can just learn to be the offset around 0 for specifically each action. And this turned out to work much better than if you don't do that. You could still just put that into the architecture. So as far as the learning algorithm otherwise is concerned, we're still just doing something on some action values. So this is in some sense hidden for the rest of the algorithm that this is going on. But then you could still apply this and you could still see if that helps. And let me show you a video. I don't know whether I'm going the right direction with this one. No, wrong one. This one. Okay. And I don't know how clear this is on the screen. I'm going to just quickly tone down the lights, I hope. I don't know which button does what, so bear with me. Okay, this seems to be working. Before I play the video, I'll tell you what you're going to see. What you're going to see is 2 visualizations of the agent running on the same game, which is a racing game. You're the car at the bottom there, and you can basically go left and right to avoid bumping into things. Superimposed on each of these screens, there will be some reddish blobs. These reddish blobs are the gradient with respect to the input of either the value side of your action values or the advantage side of your action values. What that means essentially is we're looking at how much attention are you paying to specific pixels of your screen to predict your value, and on the one hand, that's on the left, or to predict your advantages, that's on the right. And what you can then see is that there's a lot of attention in a sense. Well, you see these flashes, and you can kind of see it now there. So what you'll see on the right-hand side, it's a little bit less clear, and it's more sparse, the signal, but you'll sometimes see flashes which are much closer to the car, especially when there's other cars close. Because at that point, it really matters what you do, which means that the advantages, they really care a lot about what happens there at the bottom of the screen. The value on the left-hand side is then the state value, which we decomposed from the advantage, and the right-hand side is the advantage. And then together, if you would add these together, you would get your action value. Thanks, that's a good question. Yeah?
Earlier you said that the state value could increase while all the action values decrease, or vice versa. Could you just explain that?
Yeah, sorry. I said that this could happen if you don't do anything else, but then I said what actually happens in practice is that when we do this, when we create our action value, we subtract the mean advantage, which means that now they can no longer do that, because if the value would then go up indefinitely, the advantages could go down, but the subtraction of the average means that that doesn't do anything for your action values, which means that if the value now goes up, your action values will just become wrong. So now the value function is actually basically pegged to the true value instead of being able to go up and down. And that's an important, basically, implementation detail that you could think of it like that. It's an important part of the algorithm. So this is the way Rich likes to depict these things, where these round circles depict states, and then the solid circles depict actions. So normal temporal difference learning would start in a state, would take one action, would bootstrap in the next state, and then you could consider doing this for 2 steps or more steps, and in the end, if you go all the way to a terminal state, which is depicted here by a little square, let me turn the lights back on, sorry, then you have Monte Carlo. Now we talked about how to then apply this within the temporal difference learning algorithm for prediction, in which case we're considering doing this basically, all of this is conditioned on a certain policy. There's a certain policy you're following and we're trying to predict the value of that policy. And then you could use TD learning, which is the one-step return. We sometimes call it that. And you could consider Monte Carlo and you can consider everything in between. So in general, we'll talk about an n-step return or a multi-step return, which you can then use as a target. And what we've seen before in the lecture where I discussed these things is that there's a trade-off, and typically you're best off not doing the one step and not doing the Monte Carlo, but somewhere in between. Now we could do something similar here, but not bootstrap on the state value, but we're just going to bootstrap with, in this case, the double Q bootstrap target. This means we're doing multi-step Q learning, but there's something a little bit maybe partially weird about this, because the trajectory before we bootstrap would be on policy, but then we're bootstrapping off policy with respect to whatever the current greedy value, or sorry, greedy action is according to your online action values. That's still okay. This is less greedy than the normal thing, but it's still a policy improvement step. In fact, even if you would be fully on policy, typically we do some exploration with, in this case, epsilon greedy, which is already a way to be a little bit greedy with respect, in some sense, with respect to your current values, which means even in that case, you'd already be doing something which is akin to policy improvement. But especially here with the bootstrap target, which is off policy, you're doing policy improvement. And it's also still a well-defined prediction target. It's just a little bit of a more unconventional one, where the prediction target is now, the semantics of the prediction target is now, what if I'm on policy for a number of steps, with, in this case, the epsilon greedy policy, and then I take the greedy action? Which is maybe a bit of a weird question to ask, if you would just be posing questions, prediction questions. But it's a perfectly valid one that you could learn about. And then you could still hope to have the nice trade-offs between TD on one hand and multi-step or Monte Carlo learning in the other extreme on the other hand. Okay. So now I'm going to go into depth, into a little bit of depth at least, into something which is a little bit more technical, which is distributional reinforcement learning. I mentioned this all the way in the first lecture. But I didn't explain how it works, so now I'll explain a little bit how this works, or at least one instance of this, because there's now also other instances and you could probably imagine more. This is a fairly recent thing. The citation up there says 2017. People have investigated or considered similar things in the past as well, but this is a very nice example where it also showed like a nice performance boost by doing this. And the idea is to basically go beyond expected cumulative rewards, which is the thing that we've been learning so far. The expected cumulative reward could be on or off policy, but it was still this one thing that we were trying to predict. And the realization is we could also try to predict other things. For instance, we could try to predict the distribution of the returns. Instead of just this one mean of it, we could try to basically somehow capture more of the structure of this return. Knowing this might be helpful for some things, and I deliberately kept that a little bit vague. For instance, you could reason about the probability of termination. Let's say your actual reward function is always 1, or maybe it's always 0 and it's 1 or -1 when you terminate. Then you can maybe reason about, okay, what's the actual distribution of these things? How likely am I to terminate when I go here or there? Which might be useful, for instance, if you're doing something where you need a little bit of safe exploration, perhaps, where you don't want to necessarily go to places where there's a probability that you might terminate or your robot might break down. So sometimes these sort of things are considered in that context. You could also even consider to having risk-seeking agents rather than risk-averse agents. One thing to note though is that this distribution of returns doesn't give you your uncertainty, it's actually the distribution of the returns from this state. So it's not about how much do you know about this state value. You could have a lot of uncertainty about an expected return. But instead, this is basically trying to capture, even if this distribution is irreducibly high variance, right? There's just noise in the environment, and you can never collapse this distribution to a single point if you want to capture the full distribution. It might just remain like that, even if your uncertainty about what the distribution is goes down. That's a distinction that I just want to make clear. But it's still a lot of things that you're trying to learn in addition to the average things, which means, for instance, that your representation might be forced to learn more, which might maybe not necessarily immediately sound like a good thing, but it actually is, especially if the normal signal is quite sparse or low information, which it often is in reinforcement learning. We just have this one scalar signal that we're trying to predict. And then maybe trying to learn more about it just gives you more learning signal to update all of your weights in your deep neural network. So this can speed up learning, because learning more about each sample potentially means you need fewer samples. Of course, you need to be a little bit careful about these things. If you try to learn things that are completely unrelated to the thing you actually care about, then you might find that you're using certain function approximation capacity and you get inference and things get worse on the thing you actually care about. But in this case, we're learning lots of things which are quite related to the thing we care about. Even if we're only interested in the expected cumulative reward, even if we're not interested in risk-seeking or risk-averse agents, then still these things are fairly well aligned, and we might hope that our network just learns faster. So an example of this is categorical DQN, or C51 it's called in the paper. And in this specific instance, there will be a fixed finite support on which we're considering the values to be able to lie. So the support here was picked explicitly for these Atari games to be between -10 and 10 with increments of 0.1. I hope I did that correctly. Probably not. It must be that 51 points in total. So anyway, between -10 and 10, you sprinkle 51 points. And then basically what the semantics of what we're trying to predict is, for each of these points, how likely is the value to be, is the return to be equal to that point? Of course, it's never going to be exactly equal to that point, and that's fine. So what we'll basically do is one way to interpret this is that we'll basically try to map the distribution on this comb to be as close as possible to the full distribution, which might be more continuous between these different values. So for each of these points of support, we'll assign a certain probability. I put this between quotes because you could also interpret this just as a weight, but let's call it a probability. And then this defines the distribution. We have the support, we have the probability for each point in the support. This together gives you your full distribution. And then we can, of course, use that distribution to get your, for instance, your mean action value. And in this case, this is simply just doing the dot product between your support and this probability vector that you get. And then this thing should be approximately equal to your action value. That will be one goal. And then you can use that thing to act, for instance. But the goal now is to learn these probabilities rather than just this reduction to the mean, which should mean we're capturing more structure. And so how do we do that? Well, it turns out you can actually define a Bellman equation on these distributions. And specifically how that works in this specific example is that we first, considering the next state, we'll pick, let's say we're doing Q-learning, so we'll just use the normal online parameters. You could use the target parameters if you want to do double Q. But we'll pick the greedy action in the next state according to the mean, let's say. And then what we'll do is update the support, and this is depicted here on in the picture on the right, which means we have a certain distribution, which is here depicted as a bar plot, but it's actually more like a comb, but this is easier to visualize. And then what we basically do, we first shrink that according to our discount factor, and then we shift it according to the reward. So we're basically just moving this around according to the sample that we got. This is for the one-step case. Then this new distribution, which is depicted in green there, at the bottom left, it won't actually map onto the support that we had. So we need to do an additional step there, which is basically to map it to the closest distribution on the support that we're allowing, on these points that we defined, which is a projection step. And then we have a new distribution, which is defined on the same support that we already had at the beginning. So now we can say, okay, the distribution of my current state action value needs to be closer, in a sense, to this distribution. You can consider this basically your target. In the normal expected case, this would be, say, reward plus discounted next value. But in this case, it's now a distribution that we're updating towards. That's the way to think about this. And then we just use that basically as a target. But in the normal case, we can do a squared loss, essentially. We update our value towards this target. In the distribution case, it's maybe more appropriate to use something like a Kullback-Leibler divergence, which is a typical thing that is used to match distributions onto each other. This is basically, you can think of it as a loss on distributions where you normally use the squared loss, if you're not that familiar with these. So essentially this part here, which is in the picture, which is from the paper that I cited up there, shows you the first 3 steps, and then you still need to update your parameters to have the distribution at your previous state in action to more closely map to this distribution at the next, after the 1 step, at the reward in the next state. So for details, I would definitely suggest you look at either the rainbow paper that I cited, which gives you the very short version of this, or of course for more depth at the paper that introduced this. I understand this is a bit fast, but the idea is hopefully a little bit clear. Which then brings us to the final component, which is noisy networks. And the idea is here to hopefully improve the exploration. As mentioned, DQN used epsilon greedy exploration, which might not be the most appropriate. It basically just picks greedy all the time and every once in a while picks fully random, which might be a little bit of an uninformed way to pick. Because you might know, for instance, for sure that this one action is horrible and you should never take it. Epsilon greedy doesn't know. It would just randomly take it every once in a while. So we learned that, say, UCB is better in bandits, but that's hard with function approximation, as I explained, because it's hard to capture these counts. There's actually work on that, trying to do UCB-like things in the deep reinforcement learning case as well. But instead here, I'm going to talk about a different proposed solution, which is to add noise to the parameters, essentially. So normally we have, say, a linear function. This vector y is a linear function of x, where the weights w and the bias b are the things that we're wanting to learn, let's say. So this is a linear operation which also happens within these deep neural networks. Specifically in the DQN case, we typically have 3 convolutional layers, which for the purpose of this thing you could consider, but we'll just skip over, we'll not consider. And then there's 2 fully connected or dense layers, which are basically linear operations like this. And there's a nonlinearity in between, but we're not looking at that part. We're just looking at the linear part there, which basically means you're looking at the features going into a layer and then at whatever the output is of the linear transformation of those features before going into the next, say, nonlinearity if there is one. And then what we'll do is we will replace this operation with a different one which is also linear, but we're basically adding additional inputs in some sense. And those are these epsilons, epsilon w and epsilon b, which in the epsilon w there is a matrix of the same size as your weight matrix, and the epsilon b is a vector of the same size as your bias vector. So basically the same size as the vector of the linear layer. And then the idea is that we have separate weight matrix w prime and a bias b prime that multiply with these noisy inputs in a sense. Component-wise. So you could of course also imagine just having one input that maybe goes into all of these things, but in this case it's done component-wise. And what will happen then if you train this thing? Well, eventually the network should learn that these things are just noise and you should ignore them. So it should set, probably in the end, it'll set these w prime and b prime parameters all to 0 to ignore the noise. Yeah?
Why wouldn't we just add noise to the weights and biases themselves?
You
couldn't be learned to be set to 0, right?
You can add noise to the weights and biases themselves as well, yes. But the idea is that you have to tune how much noise there is, and you want to reduce this noise appropriately somehow, which you might then want to fix. And what we're going to want to exploit here is that actually learning takes care of that. It will set the weights to 0 appropriately over time, but especially for things you've seen often.
Do we need to set learning rates appropriately for these W tick and B tick?
We're using the same optimizer to update both our normal weights and these additional weights. And the idea is basically to exploit the fact that the things you've seen often, they will interact more heavily with the noise, which means that you'll tune down the noise more quickly, which means that for, say, feature vectors x that you've seen very often, in effect, the noise will be quite small after a number of updates. And this might give you appropriate exploration, because it means that for inputs that you haven't seen a lot, you'll have more noisy outputs, which means you might do more random stuff. But if you've seen certain inputs a whole lot of times, then maybe the noise has disappeared, and then you learn not to explore there. You will be greedy there. So one consequence of this is that you're not necessarily equally greedy or equally exploratory in all parts of your state space, which maybe is a nice property to have. I'm not claiming this is the only way or even the best way to do this. I'm just saying this is an instance of something that you could do, and it has been proposed. And so it was proposed in a separate paper, as all of these components were. And what we're investigating here is how these things then play together. So what if we combine this with all the other components? In that paper was actually a nice demonstration. They took a number of different algorithms, including DQN, but also including the actor-critic algorithm that we discussed in the policy gradient lecture, and applied this idea to these different algorithms. And in all of these cases, they saw some gain. Okay. So, yeah.
Does that resemble a Bayesian neural network quite a lot, because it's kind of like adding variance at the beginning and then slowly cutting off?
Yeah. So the question is, does it resemble Bayesian neural networks? And indeed, this is very related to things that are, for instance, sometimes called Bayes by backprop or other Bayesian networks. The idea is very similar. Whether you want to view them as a Bayesian thing or just as an uncertainty thing, maybe less well grounded in the Bayesian part, that's more or less optional, but it might very much inspire where you go next, right? Which variants you might consider, and there might be ways to exploit a lot of the knowledge from, say, Bayesian optimization to be able to think of other ways to do this and maybe improve. But yes, it's a good way to look at it. It's a nice way to look at it. Okay, so I think this was a good point for a break. So let's break for 5 minutes. Okay, so it'll come as absolutely no surprise that we can successfully combine all these methods. So that's the top line there, rainbow colored line. To briefly explain what you're looking at in this plot, there's a line at the bottom there which is maybe not that easy to see, but it's a gray line. That's the original DQN paper. That's the original DQN algorithm, I should say. And the x-axis here is millions of frames in each of these games that you've seen. And the y-axis is a median human normalized score, which means there's a professional games tester that played all of these games. And what we're saying is basically we're pegging whatever score that person got on each of these games. We'll say that's 100%. And then we'll play a random agent. We'll say this is 0%. And this gives us a way to maybe meaningfully combine the scores of these different games. Because otherwise the scores of the different games are actually very variable. Some games have scores in the millions. Some games have scores in the single digits. And then it's hard to combine these things. So instead what we'll do is we'll rely on this human tester to give us an appropriate scale. So what that means is if in a specific game you get 100%, that means you did as well as that tester. It doesn't mean it's the best possible or anything. In some games it is. I mean, on something like the game of Pong, that's not a very hard game. So you're pretty much almost optimal if you played it for a while. Other games are much harder, and this tester also the testing was done under fairly constrained conditions, so he didn't get unlimited time to play every game before he was tested. But 100% is then a good maybe indication of what's a relatively average human. If they put a little bit of effort in and they're relatively good at playing these games, what score would they get? And what we see here is that the performance of DQN by this rainbow algorithm is attained in 7 million frames, whereas DQN took 200 million, which means that learning is like roughly 14 times as data efficient and fast, because this algorithm isn't actually taking that much more compute. The algorithm is actually slightly slower to run because of the distributional updates. Although there's ways to maybe speed those up, you're actually also just outputting more stuff, so there's a little bit of a speed loss there. But it's roughly on par. So the algorithm, it doesn't run that much slower, and here we're basically looking at the data efficiency. which is a huge gain, of course, more than an order of magnitude. The other lines here, the yellow line is the A3C algorithm, which was notable because it was able to run without experience replay on multiple processors at the same time. And by doing that, it could actually blaze through quite a lot of data, but it's not actually that data efficient. And one reason for that is that it's not using experience replay. So A3C is barely more data efficient than DQN. In fact, the learning curve goes up slower, but then it goes a little higher at the end there. But if you look at wall clock time, it's fairly efficient though. Then the different algorithms or components that we discussed are in there, but I should also point out here that, for instance, the noisy DQN line there just adds noisy networks to DQN. Then above that we see the double DQN algorithm, which just adds double Q learning to DQN. But then a couple of lines above that we see prioritized double DQN and dueling double DQN and distributional DQN. And these, I'm not 100% sure of the distribution one actually, but the prioritized and the dueling do use double DQN. So they weren't using only this one component, prioritized or dueling, but they also added the double. So these are not the specific components completely detached from each other. There's some combinations there. But we can see, so the main thing here is basically to compare to the actual published algorithms in each of these cases. But what we could also do is we can take that rainbow algorithm and then we can take away each of these components. This is called an ablation study, where we have a bunch of new stuff, right? We can't look at the full Cartesian products of all the combinations, but what we can do is we can consider roughly what this one is doing. Like I said, it's not exactly doing it, but it's considering if you start with the baseline and you just add each of them, what happens then? This plot is basically saying what if we start from the thing that has all of them and we take each one away? And what then remains? And that's also quite interesting to look at. And the way to interpret this plot is to look at the lowest lines here. Basically means that that component was really important in this combination. So the lowest three lines there at the bottom are, in yellow it's the multi-step learning, in blue it's the prioritized replay, and in orange it's the distributional RL. Whereas especially the blue and the yellow one, learning is also quite a bit slower there at the beginning if you don't have those components. Then there's the noisy networks, and somewhere more up there we see the dueling and the double components. So one conclusion is that these components work really well together, and that maybe in this specific combination the most important components were prioritized replay and multi-step returns, and to a lesser degree the distributional reinforcement learning. Yes? So no noisy means we do epsilon greedy instead? Yes, if there's no noisy we do still use exploration, but we're basically swapping these out. Yes. That's a good question, thanks. And in this setting, the least important were double and dueling, which was maybe a little bit surprising because both of these gave a huge boost in performance when they were first proposed. But one way to explain that is to look at the full system. What is it actually doing? And in this case, there's actually no way to wildly overestimate your values because we're doing this distributional RL, which means that we have a fixed support. And in this case, the support was, like I said, between -10 and 10. So you can literally not represent values that are higher than 10. So that sounds like it's a way to combat overestimations, but it might be a bit arbitrary. Where does this 10 come from? Well, this requires you to know an appropriate range for these values. Different games have very different scores, as I mentioned, but what turns out to be the case is that in basically all of these algorithms that I just discussed, we have been clipping the rewards. Which means that we're not actually looking at the difference in score, we're not actually optimizing the actual score in these games, but instead all of the rewards were clipped to -1, 1. Which means, for instance, that in a game like Pac-Man, where you eat pellets and you can eat power pills and you can then chase ghosts, the algorithm has no way to see the difference between eating a pellet and eating a ghost. Whereas for the actual score, there's actually quite a big difference between those. So this was done to make learning easier, but it does change the objective. And it might lead to different performance. So is there a way not to do that? So this wasn't in the rainbow, but there is actually. I mean, there's always more components that you can consider, so we couldn't consider all of them in the rainbow. But one way to do that is to normalize targets before you do an update. So the thing to note here is that in online reinforcement learning, you don't have access to the data set in advance. And why was this maybe an underexplored topic? I think it's because in the supervised typical setting, or especially in classification, you don't have any issue of scale. In classification, you know that everything's between 0 and 1, say, all the outputs of your network. But even if you're doing regression, people typically just normalize the data and then do the regression, say, which is an appropriate way to do this if you have a data set. But if these things change over time, then it's much harder. Because in these games, for instance, at the beginning your scores might be quite low, but it might still be important to see the difference between an extremely low and a somewhat low score. Whereas much later in the game, your scores might be thousands of times higher in certain games. And then it becomes a little bit harder to pick an optimizer and a learning rate and things like that to be able to learn across all of these different scales. Because typically we tune our learning rates and other parameters to be appropriate for the scale that we're at. We can just, sometimes it's not even that we normalize based on the data set, we just tune our step size, which is fine if you have a fixed data set. But in this case, it's less clear that that works well. And it turns out it actually doesn't, which is why we were clipping the rewards. So a proposed solution here is to adaptively normalize the updates. And the specific algorithm here is fairly simple, I would say. It has a more complex component maybe at the next step. Also not that hard, but so I thought I'd walk through it explicitly. It's more general than the reinforcement learning setting, but of course applied here in the reinforcement learning setting. But maybe it's more generically applicable to regression in general. So we'll just consider a target, which I'll call T. And T, for instance, could just be your one-step Q-learning bootstrapped return. And then the idea is simply to have some normalization parameters. For instance, you might keep track of the first and the second moment, from which you can then reconstruct the variance. Of course, you might need to be a little bit careful here on this last step. I didn't put it on the slide, but you have to, of course, make sure that this estimate of the variance is never below 0. There's just numeric things that can happen, so you might want to do a little bit of checking when you actually code this up. And then there's just some step size on these statistics. So typically this is not that hard to tune because you basically just want to have a rough feel for where the mean of your targets is and where the standard deviation of your target is. And the idea is then to basically consider an update. For instance, proportional, this would be for the squared loss. Your update could be proportional to where you take that target, you just subtract the mean, you divide by the standard deviation, and then you update the outputs of your network towards that. Which means that this is, say, roughly centered around 0 with roughly a standard deviation of 1. It doesn't really matter what the targets are. One little thing to note here is that you can actually do this, and that's also what happens there. You can update your statistics before you even normalize your target. Which means that the very first time you see an extremely high reward, you can already correct for that before you do your updates, before breaking your network, before scrambling your weights in a sense. You can still recover, of course, the unnormalized target by simply just multiplying with the standard deviation and then adding the mean back in. And that's also what's used up there for the bootstrapping. Because this is important because the rewards are of a certain scale. So to construct a valid target with bootstrapping, you need to be able to recover the unnormalized targets. But that's fortunately very easy to do. Now this is very simple. You could just try this. But turns out maybe that doesn't work that well, because a naive implementation of this would change all of the outputs of your network everywhere whenever you update the normalization. And that might not be the right thing to happen, because you might be in a certain state right now, or especially in the online case, you might be in a certain group of states where the rewards are, say, fairly high, and then you're updating your standard deviation, maybe your mean, things like that. But this would immediately also change your outputs for the network in states you visited a long time ago where you're not right now, because you're just multiplying these in to get these unnormalized values. So there's an additional part of this algorithm which basically says maybe we should just change our network whenever we do that to counteract the change to the statistics. So now we're only using the statistics to change the updates to the network, but we're not changing them to change the outputs of the network. And the way to do that is, or a way to do that, is to basically realize that this unnormalized output of your network, sorry, the normalized output of the network, this Q tilde, which on the previous slide I defined as the output of the network, the thing you're updating, it's typically a linear function. In the DQing case, we have a couple of conv layers, then we have a fully connected layer, we have a ReLU in between, but then we have a linear layer which goes into your action values. So you can write that like this, where there's just some weight matrix, multiplies your state features, adds a bias, and this gives you a vector of your action values. The action isn't there because it's basically implicit in the dimension of your vector that you output. And then there's basically a simple idea here, which is to change this thing, not with a gradient update, but literally just applying these definitions here, into a W prime and a B prime in specifically this way, because whatever your sigma t plus 1 is and whatever your mu t plus 1 is, this will keep the output exactly the same as it was before. So if you change your weights in one way and you basically change the normalization up there in the other way, you basically change them in opposite directions so that the total output is unchanged. And you can exactly do that because all of these operations are just linear. So you can literally just keep the outputs in exactly the same situation no matter what happens to the normalization. That's nice because, again, for the case where you get a really big reward for the very first time, there might actually be quite a big update to your normalization, which might otherwise still be harmful for your network. So by doing this, you basically make sure that the output don't change, but the gradient going into the network is still appropriately scaled down. And then you update everything as normal, just using stochastic gradient descent or Atom or RMS swap, whatever optimizer you prefer. Which means that basically these weights now are updated twice. Once to counteract the normalization and then once with a gradient update. Now the question is, does this work? So I called this pop art for preserve outputs precisely, which is that second step, while adaptively rescaling targets. It's a bit of a silly name, but it's nice to have a label to be able to refer to these things. So now we have a word that we can use to refer to it. And what you see here on the left is on these Atari games, essentially. On the x-axis you see millions of frames. And on the y-axis, sorry, there's a number of different lines plotted there, dotted lines. And the y-axis shows you the norm of the gradient on a specific game. So there's a number of dotted lines there, which is not really that easy to see. But what these filled in regions basically are, they're like the 50%, 90% and 95%, I think, portion of games that fall within that region. And the y-axis there, which is the norm of the gradient, is on a log scale. So what we can see if we don't clip the rewards is that the gradients going into the network are basically 6 to 8 orders of magnitudes apart for different games. Some games they're like below 1, the norms of the gradient. Some games they're in the millions. That makes it very hard for optimization. Turns out we haven't really figured out optimization that far yet that we can handle these things very elegantly. So if you then clip the rewards, which is the middle part there on the left, you see that these norms are much smaller in terms of range. They still span like maybe 2 to 3 orders of magnitude, but it's much more constrained range than before, and especially they're capped at the top. You don't get these extremely large gradient norms, which means it's easier to tune a step size that works across all of these now. And this is what was done in, say, DQing and all of the follow-up work to that. But if instead you apply this adaptive normalization scheme, the gradient norms are even smaller, in smaller band, which means that maybe it's easier then to do the optimization. Now, if you apply this in the full setting, so this was applied in this case to double DQN, which is added on as a component, and turns out you get this distribution of games. What this shows is basically the relative performance of the algorithm with pop art and without, where above 0 means with does better and below 0 means without does better. And surprisingly, across these 57 games, it's basically on par in terms of the median and the mean performance, but there's huge differences per game. Some games are way better, and some games are way worse. Now, that might not sound like an immediate win, because why have we lost some games? Why are some games way worse? My explanation to that is basically, we can look at the video now, is that the games have become harder in some cases. So this video again explains basically the settings. So the rewards were clipped to +1 and -1, which makes everything easier. And this is what then happens if you run that on Pac-Man. This is basically the original double DQN. And what you see the agent doing is it's eating pellets. It's also eating these power pills, and this turns the ghosts blue, which means you can eat them for points. But then it completely ignores them. It doesn't chase the ghosts, doesn't try to eat them, even if it's very close to them. Well, if we get better at these things, if we have better reinforcement learning algorithms, obviously doing the right thing, going to the next level, should be able to give you more reward. But in this specific case, it didn't. And there's a number of other games that are like that, where basically it means that the optimizing the score when it's unclipped is actually harder to do than optimizing the score that is clipped, and this might lead you to worse performance. So this is popping up a level. We want our agents to understand and interact with the environment. And as mentioned, a single reward signal can be quite sparse and low in information. So we want to learn many things. I mentioned this in the context of the distributional RL, where we're learning basically distribution of returns. But there's more that you could predict. So the idea here, this is from a paper called Horde. Well, it's a longer title, but the idea is called maybe Horde. Is that you have some, you could think of this learn function in the middle as agents. I just put learn function, didn't quite know what to put in that box. But the idea is that this is your learning algorithm essentially. There's data coming in, a stream of sensory motor inputs on one end, and there's a bunch of predictions now coming out at the other end. One example is the distribution RL, but you could think about many other things as well. There's a dotted line here as well, which means you might also feed these predictions back in and predict things about your predictions, which might seem like an odd thing to do, but it's perfectly valid, and it might actually be quite a nice way to build up knowledge, where you're now trying to, let's say some of these things that are output are more like features, and now you're predicting the long-term features. So what are we then predicting? Well, the key idea is basically something that is called a general value function. So we've discussed value functions a lot, but we've basically only been talking about value functions over rewards. The idea is that a general value function is something that is conditioned on more than just the state in action and implicitly on the reward and the discount factor. Now we're going to be explicit about that. We're going to define something C, which is a cumulant, which is there in the subscript all the way at the left. A gamma, a discount for this cumulant, and the policy that we're considering. Now one thing that we already considered is if you just take your cumulant to be a reward function and your discount function to be the standard discount, maybe it's undiscounted, who knows. We already discussed you could learn about different rewards. You might use, say, importance sampling to do that in practice. It might be an interesting question. What would happen if I would follow this reward? But what this is saying, you could actually also consider other signals to predict about. For instance, you could predict what is the heat of my motor when I'm doing certain things with a robot. How does that progress over time? How does that change over time? Or you could predict how much rain is going to fall over a certain period. And you could think of all these questions that you could come up with over certain horizons, which is then decided by this discount factor. And this could be useful knowledge in some sense. In fact, there's this, basically, you could call it maybe the hypothesis or an idea that Rich Sutton likes to say, which is, if you can predict everything about the world, maybe that's all you need. Because it's hard to imagine other knowledge if you can already predict everything. So how could other knowledge then still be useful? Or is there even other knowledge that you can consider that is useful, apart from all the predictions? Of course, it's a bit of a, there's a caveat there, because all the predictions is quite a lot and hard to learn and hard to pick and hard to represent. But maybe the principle is sound. So what we call this, we have this cumulant, which is basically the stand-in for the reward function. The discount factor is sometimes also called the termination or the continuation parameter, which is now also a function of state, so it can differ from one state to the next. And then pi is your target policy. It's an open question how to pick these, what things to appropriately represent, what things to predict. Yeah.
So the cumulants are part of the state, right?
The cumulants is a very good question. Are the cumulants part of the state? I need to probably be a little bit more precise here. The cumulants are definitely part of the state as a whole, so including the agent state and the environment state, because otherwise they're not there, right? They need to be signals that you're predicting. They could just be part of, say, your raw inputs. You could be predicting pixels. They could be part of your agent state. You could be predicting features. All of these are sound, but they must indeed be real signals somewhere.
So that also means this is basically, it would be subsumed by a model of the environment, right? Because there we would predict all the entire next state, and here just a subset of it.
So is this subsumed with the model of the environment? That's not completely true, because as I said, you could also predict functions of state. And in addition, a model of the environment, but I actually have a slide on that, so I'll go back to that. Model of the environment can be considered one-step prediction. But here we're considering maybe more generally to also allow multi-step predictions and also under different policies. As far as the cumulants go, there's some truth in what you say, that these cumulants, they need to be somewhere in your input in a sense. And the input, you could consider the input to the algorithm both the raw observations and your current agent state, which is something that you build up yourself. Right? And if you allow for that, then yes, the cumulant must be part of that or a function of that. So this is an example, recent example. Maybe the more general idea, which is also the title of this slide, is universal value function approximators, which is basically just, we have these general value functions, we might want to do something with them. So now can we maybe learn these? Can we build function approximation techniques, or can we build functions that actually capture this? And one key idea of the universal value function approximations is to basically feed a representation of, say, a goal. In this case, I only took two of them, the cumulant and the termination, and together you could call that a goal. You don't have to. In some cases, it's appropriate. You could feed a representation of that as an input to the network. And what's nice about that is that the network could then potentially learn to generalize over this input, which is a little bit different from the picture that we had for the horde, where maybe they were kind of like depicted separately. But you could just think about these things. I mean, here at the output side, these predictions are basically separate lines here. But you could also think about this as being the predictions are answers to different questions that you're asking, and the question could also be an input to your network. And then the network could maybe learn to generalize over this input, which means you could also ask for new cumulants and termination conditions on the fly and hopefully get already a valid answer. The idea is that this allows generalization across tasks and goals within an environment. One example of that last bit there is there's a recent paper by Dan Mankiewicz and others in which they set up a situation where the actual goal is to, say, get a chest. But in order to do that, there's this sequence of things you need to go through. You basically first have to collect keys, because with the keys you can then open a lock. When the lock is open, you can open the door or something like that. You need the lock for the door in some sense. And then you can go through the door and you can collect the chest. That's basically the let's say the abstract situation. In reality, what was happening, what the agent was needing to solve was to collect certain objects, but for an object to be rewarding, it first had to collect a different object. And there were sequences up to length 4, where basically for the chest to be rewarding, you had to get the key, and then the lock, and then the door, and only then the chest was a rewarding event. If you would grab it immediately, it wouldn't be rewarding. If you learn this from scratch and you only focus on these chests, it's very hard as an exploration problem, because there's basically no way that your random exploration without any feedback will learn to do exactly this sequence of things unless you throw a whole lot of data at it. But then, even then, in some cases, you make it so hard that it just basically never learns this. What you could also do is you could optimize for all of these things separately. You could have a component that tries to predict and optimize grabbing just keys. You could have a separate component that tries to optimize the locks and the doors and the chests. And what then happens is at first this chest component will basically give you no direction at all, but the keys might be very quickly learned as a rewarding thing in itself. Oh, I just go and grab that. I get rewarded. I don't know why. I just do that. I grab the reward. But then when you have the key, all of a sudden the locks become rewarding. So then all of a sudden your random exploration might just bump into a lock and you might find, hey, that actually felt good. When I have the key, the lock is good. And now I can learn that. And now I can more directly go to the lock. And then the next time, it might have gone through the lock to the door and so on. And that's basically what this picture here on the right shows. That you get more performance, which is basically the magenta line here, than if you do a baseline which doesn't do this structured way of predicting multiple things at the same time. So this is one way to use these multiple predictions. You could just be predicting many things that could be useful, maybe act according to them occasionally, and see if this gives you better exploration by switching between different goals than just jittering randomly with your actions. Again, this is not necessarily the final word on this. It's probably not the final word on this. And there's many different variants you could consider here, but it's just an idea, a way to think about these things. And now going to the models, as appropriately asked already. So a transition model is a specific set of general value functions, where now the cumulants are your components of the state, and the termination / discount is 0. We're only looking typically at the one step. Of course, you could consider multi-step models, but we've mostly considered one step. The models are often action conditional, which means we don't even have to care about the policy. So the policy is basically irrelevant because conditioned on the one step and the fact that you terminate immediately, it doesn't matter what your target policy is. So you don't have to care about that. Similarly, an expected reward model would also, would in this case use the normal reward as a cumulant, but would also put determination as immediate. So it wouldn't try to do the long-term things. And there's something nice about both of these in the sense that these terminations are 0, because it means that the learning task is very stationary. I mentioned this when we were talking about models. This is basically supervised learning now, which we kind of understand quite well. A downside of it is that if you chain approximate one-step models together, the errors in these models might accumulate quite quickly. So it's unclear that that actually works better than if you have good multi-step models. But then it's unclear how to build good multi-step models. So that's a trade-off maybe. The formulation of general value function as multi-step models, if we just ignore the fact whether these are easy or hard to learn, is basically immediate. You just change this discount factor or termination condition to something that is not immediately 0, and then you have a multi-step model. You could also have things that are kind of interesting, but maybe a little bit harder to reason about, where this discount factor might not be 1 for a while and then 0, but it might actually be a slowly decaying one, as we normally do, where the discount factor is, say, 0.9 or 0.99. Which means we have a multi-step model, but it could be interpreted as one where you can consider your model terminating at each step softly or with a certain probability, which is maybe different from the normal way we think about models. Rolling forward a model basically is similar now than as using predictions as input for other predictions, which is related to this horde picture that I had, where we have this dotted line going back as an input. You could chain these. You can do these again and again and again. And you could also have multi-step predictions on multi-step predictions, if that makes sense. Okay, so we're almost done. I basically wanted to stop here at the slide I had at the beginning as well. And if there's any more questions, I wanted to leave a little bit of time for that at the end, although people have asked questions along the way. So this is basically all the stuff that we covered in addition to like the advanced topics that we discussed now. In the interest of time, I had to skip over a lot of stuff. I haven't talked about exploration that much apart from the noisy networks and in the bandit setting. The other thing I didn't really talk about that much was, and I promised at the last lecture that I might get back to, was AlphaGo. I just wanted to mention that I deliberately didn't go back to that here because for one, I felt that again, it's something that a lot can be said about, and it's also something that a lot has been said about. I'd be very happy to point anybody towards resources if they want. So if you want to know more about any topic, specific, for instance, AlphaGo, but any other topic as well, feel free to let us know, for instance, on Moodle, and we can just point you in that direction. Moodle's especially nice because there might be other people who are also interested, or might even not even know that they're interested in that topic, but if they see it there, they might think, oh, that's kind of cool. So we could have maybe a collection of things there. And also feel free to share insights or resources that you bump into yourself as well. That might be quite a useful resource in that sense. Okay, so next week we'll have a guest lecture at this time slot by Vlad, who did the original work on DQN and did a whole lot of other work as well on deep reinforcement learning. The week after that, we have Dave Silver giving a guest lecture. So also if you want to bug somebody about AlphaGo, he's the person to bug. Okay, so that's it for today. Thanks.